So now listen. So the potassium, calcium, gallium, germanium, arsenic, selenium, bromine, and krypton, they are called normal or representative elements. Whereas the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, they are called the transition elements. But they are all having the common outermost electronic configuration, that is 4s. Sometimes it is 1, sometimes it is 2. See, scandium 3d1, 4s2. Titanium 3d2, 4s2, vanadium 3d3, 4s2, chromium, it is actually 3d4, 4s2, but d4 is partially completed. So in order to make it half filled, that one electron from the s orbital goes to d orbital and it makes it 4, 3d4 becomes 3d5, 4s1 to attain stability. Similarly, in the case of a copper, which is supposed to be 3d9, 4s2, is 3d10, 4s1 to make it a completely filled d shell, d subshell. Therefore, the electronic configuration, it is adjusting itself to attain the stability. So the peculiar behaviors shown by the transition elements are: number one, variable valency. Variable valency means, suppose if you take alkali metals will always show the oxidation state +1, hydrogen +1, lithium +1, sodium +1, potassium +1, all these things are having the valency 1. If you take alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, radium, they all will show the valency 2. They can form a divalent cations. If you take helium, neon, argon, krypton, xenon, radon, they show the 0 valency. They do not normally combine, they do not show any chemical combination. They are totally inert. If you take halogens, halogens are highly electronegative and they show the valency 1, that is -1 oxidation state. But in the case of transition metals, they show variable valency, very peculiar. Take, say for example, iron can assume the valency is +2 and +3. Cobalt +2 and +3. Nickel +2 and +3. Copper 1+ and 2+. Zinc 2+. And manganese, it can show variable valencies from +2 to +7. If you take a KMnO4, it is +7. If you take a chromium, it can show +3, +4. So the transition metals, they show variable valency. Why they are showing variable valency? You know, the d orbitals are non-degenerate. These are all very important idea. Non-degenerate means, you should know what is degeneracy. Degeneracy means 2 or more orbitals in the same energy level. If you take a p orbital, p orbitals are degenerate. All the 3 pre-orbitals are of equal energy. Therefore, what happens is, suppose if a p orbital is having 3 electrons in x, y, and z, if I am giving some energy to remove the electron, when I give the sufficient energy for the removal of the electron, all the 3 electrons in the 3 p orbitals will leave the system immediately. Therefore, it is possible only to form 3+ ion. But in the case of d orbitals, they are non-degenerate, means when a little energy is supplied, 1 electron will go out. When a little more energy is supplied, the other electron will go out. When little more energy is supplied, 1 more electron will go out. Therefore, if a d orbital is having 5 singly filled orbitals, each electron can be removed from the system one after the other when you increase the energy of removal. That is why the variable valency is possible in the case of transition metals. And also, the DD transition is forbidden, but they are able to form colored complexes. KMnO4 is of intense pink color. It is because of the charge transfer from ligand to the metal. So, the metal ions are forming colored complexes in the case of transition elements. And also, there are a lot of possibilities for the atoms to have unpaired electrons. Therefore, they form paramagnetic compounds. Whereas this is not observed in all other elements. Therefore, the transition elements are of very peculiar properties, like variable valencies, formation of colored ions, and also their paramagnetic nature. So they are coming in between S and the P block. That is why they are called transition elements. So you should here you should understand the difference between the representative elements and the transition elements. So the transition elements, the first row or the first series of the transition elements begins after the potassium in the fourth period. Therefore, in the first period, only two elements are present. In the second period, only eight elements are present. In the third period, only 8 elements are present. But in the fourth period, 18 elements are present because of the introduction of the 10 transition elements in between potassium and then gallium. So the transition metal is introduced here. The reason is the filling up of d orbitals before 4s orbital. So that is the important point. So if you are not able to understand what I am telling you now, from the next class onwards, I will be using the blackboard so that you will be able to understand much clearly. Now, this one, what is the fifth period? See, the fifth period, it also contains 18 elements, starting from ruthenium, lithium, sodium, potassium, rubidium, and then finally ending in xenon with atomic number 54 from 3738. That is lithium, sodium, potassium, rubidium, beryllium, magnesium, calcium, strontium. So 37, 38, and also from 49 to 54, another P block. They are called normal elements or representative elements. But the elements between 39 to 48, that is the second row of D block. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Below the scandium, ETTM. Below the titanium, zirconium. Below the vanadium, niobium. So something like that. From 39 to 48, they are the transition series 2. So there are 18 elements. But if you look into the sixth period, which contains 32 elements, which means apart from the 18 elements constituted by S block, D block, and P block, now one more block is introduced, which is called inner transition elements. That is where the F orbital has started filling up. So the F orbital is getting filled up even much before the D orbital in this sixth series. In the sixth period, filling up of F orbital commences even before the D orbital itself. And after the D orbital, again P orbital is getting filled up. Therefore, first in between S block and the P block, a transition block or the transition elements are found. Now, in between the S and the transition, the inner transition elements are found. There are 14 elements starting from cerium to lutetium. And they are also called rare earth elements because they are very rarely found in the earth crust. Therefore, from 55, 56 S block, 81 to 86 P block, and these 8 elements are called normal elements or representative elements. From cerium to lutetium, that is 58 to 71, it is inner transition elements or rare earth elements. And again from 72 to 80, they are transition metals. But as they are the cerium to lutetium, they are following the lanthanum. They are called lanthanides. And below that in the 7th group, they are called actinides. But the 7th group I am not discussing here. The reason is the textbooks which were written some 10 or 15 years before, they have a partially completed seventh period. But the textbooks which are written now, as all the elements have been found out, the textbooks are changed. Now the seventh period is a complete. But in the previous books, the seventh periods are incomplete. Therefore, I want you to refer to the latest finding, and then I want all of you to write a passage about the seventh period as an assignment. You just have the previous approach, what we have approached earlier. What are all the S elements? What are all the P elements? How the transition elements come in between? What are all the inner transition elements come in between the S and D? And you write the same description about the seventh period by yourself. You have to write it in the form of an assignment and submit to me. That is why I have left the seventh period vacant. Now, the elements are arranged in groups. Look here, there are actually 8 groups, but the 8th group is called the 0th group. So, leaving the hydrogen and helium, I have left them. Hydrogen is in the first group, helium is in the 0th group. So, I have left them because they are far separated. I have written the remaining, the first group, second group, third group, fourth group, fifth group, sixth group, seventh group, and 0th group. See the first group, lithium, sodium, potassium, rubidium, cesium, francium. They are all alkali metals. Why they are called alkali metals? Their hydroxides are alkaline in nature. And the second group, beryllium, magnesium, calcium, strontium, barium, radium, they are called alkaline earth metals, which means they are found in the earth crust, and also their hydroxides are basic, they are alkaline. Therefore, beryllium, magnesium, calcium, strontium, barium, radium are called alkaline earth metals. And the third group is boron, aluminium, gallium, indium, thallium. Fourth group, carbon, silicon, germanium, tin, lead. Fifth group, nitrogen, phosphorus, arsenic, antimony, bismuth. Sixth group, oxygen, sulfur, selenium, tellurium, polonium. Seventh group, fluorine, chlorine, bromine, iodine, astatine. From 3 to 7, they are called P block elements. And if you draw a diagonal, you can get metals one side, non-metals on the other side, and the elements found on the diagonal are metalloids. Metalloids means the elements which show both metallic and non-metallic characteristics. And the seventh group elements are highly electronegative, and they are all fond of electron to attain stability because they have incomplete p orbital, which needs one more electron for the completion of the octet. Therefore, this fluorine, chlorine, bromine, iodine, astatine, they are called halogens. And neon, argon, krypton, xenon, radon, they have a completed electronic configuration. Therefore, they do not show any reactivity, and they are called noble gases or inert gases. So the rest of the things we see tomorrow. All the best.